I'm Anat Heilper. I'm Director of AI Architecture at Vast Data. Prior to that, I was roughly 13 years at Intel, where I was Director of AI Architecture for GPUs and accelerated AI computing. Prior to AI, I really love to learn and technology, and every 2 years I would try to switch domains to learn more. And when I got introduced to AI, you have so much to learn, so you don't need to switch domains because it's continuously learning as you go. So I came acquainted to AI at 2014 when my previous job at Intel offered me to join a cool secret project. So of course I said yes. Back in the days, the dominant models were CNN, convolutional neural networks, which was dominated mostly by, matrix multiplication and recommendation systems. The ecosystem of software was not mature. The emphasis was not on how to serve models and deployment. It was mostly to be able to execute something. You had production scale so the hyperscalers like Google, Facebook, Amazon, and so on, but not enterprises barely use them. They have a lot of machine learning deployment, like classical machine learning, but not deep learning deployment, which is not what's happening now, that everyone has a deployment. And once you do a single API call to ChatGPT, right, it's deployed inference. So everyone uses it. It was a turning point, right, in 2012, because the ability to use GPUs in that way that we didn't think of before. So CPU is an amazing engineering work for general purpose compute. You can do everything with CPU, but it wouldn't be as efficient, right? And GPU enables you to do a lot of parallel programming, which is classical for the AI workloads that we use today. This shift keeps increasing, right? You can see it in the ratio of the GPUs that are used in data center versus the CPUs, right? The gravitation leans toward the GPUs and AI specific computation like ASICs and other companies as well, right? As the AWS accelerators or Cerebras, Sampanova, and so on. So the market is leaning over the AI workloads more and more. I think it's a question of the blanket is too short. I mean, it really depends what is the main pain point that you have. I mean, there are use cases where latency is the number one problems that you have. If it's not real time, then no matter the accuracy, your solution is not good enough. There are workloads that you can have it run for a batch on the night, and you don't care about the latency, you care about the throughput. So, and you have use cases where you're power constrained, right, on the edge, for example. So it really, really depends on when you're running. For the supercomputing and hyperscaling, I would say that the latency, the requirements needs to settle down between latency, throughput, and power, because you will be always restricted by power. And a very hungry power consumer is GPUs, right? So if back in the days you wanted to reduce the model in order to use less nodes, now the dominant is the energy consumption, and then you have all sorts of optimizations to use GPUs only when you need it. This is why you have the disaggregation architecture between prefill and decode. You have KV cache. You have all those optimizations that you do to minimize the energy consumption where you really, really need it. KV cache is both for latency, right? Because if you can reuse computation that you already did, it would be much faster to retrieve it from memory versus doing the computation of the prefill. So it reduces the latency, but it also enables you to use that GPU for other computations that were needed. So you save both on latency and on the overall energy consumption in that respect, because it's much cheaper, the energy of the storage versus the GPU for the same amount of data. I think there are several ways to solve it. First of all, on the architecture itself of the GPU, which I'm not an expert with, but as time goes by, you get more efficient in the architecture that you build. As you have more efficient process in the hardware, then the energy consumption is reduced. I imagine that in time we will be able to build more efficient models. So if the models are smaller, then you have less computation and you need less parameters and you need less energy in order to get the same accuracy of what you need of the use case. And the third is also the software. If you are able to optimize on the software level of the deployment, if we do batches, if we enable to reuse computation, all of those, then it can also help to reduce the energy. So it's a multifold way of optimization. One of the fun stuff that we have in this time that everyone can build a prototype and play and code and generate code, even if it doesn't have a rich coding background, right? And you can actually have something that works. You can build an app with prompting, which is amazing. It's so much fun. The confusing part is that doesn't mean that it would actually work in production, because there are so many things that can break. When you do this vibe coding, most likely you wouldn't make tests to check for error cases. You wouldn't check security flaws in the application. You wouldn't check what happens at scale, and all of those stuff that happen in reality that would just make your workload crash. This is one aspect. You have access to database. What happens with the scale of the database? What happens with the cost of accessing the LLMs that you need in production that can scale very, very fast? And then you need to think, which model do I need to use? Maybe I'm using a too big of a hammer for the use case that I need. Maybe I don't need the latest and greatest LLM. I can just use a simple one. Maybe even some model on my client computer, not an LLM call. So there's so many different aspects that you don't think of when you just write this cool app and vibe code it. So first of all, at least the current architecture that we have now in 2025, those LLMs are statistical models. They hallucinate. You need to be able to make sure that they have correct answers that you anticipate that they would produce. So you need guardrails to check that. Because this is one thing that you didn't have in web apps, right? If you deploy agents, then they run and they have their own free will, and they can access, the web. They can access on your behalf private information unless you prohibit them to do that, which web app application could not do that. You need to be able to see that how long they run. It's not deterministic in very levels of, whether it's in computation, in permissions, in the quality, in the accuracy. All of those aspects did not exist in our regular deterministic applications. And we need to be able to know how to protect ourselves from that. I'm not sure that agent to agent would be the protocol that is sustainable, because it's a point to point. If we think about scale of agents, that if you do only point to point, then it doesn't scale, right? Because the communication overhead will be huge. I would imagine that a lot of communication would be through memory, and then you need to manage the access permissions for all of the agents, how they communicate and notify one another. But even with agent to agent, the creativity that they would have in the access pattern is not something that you can predict, as opposed to microservices. I imagine them as like little hackers in that respect, that you need to do much more verification and validation of what they do. How do you do capacity planning for that? There's something that we need to figure out. And if we don't know to analyze it in advance, we need to be able to restrict the agents. I mean, if you have a swarm of agents, not I'm guessing not all of them are created equal. Some of them will have priorities over others. And you want to be able to make sure that you don't have noisy neighbor effect and all of those stuff. So now you need like an operating system for the agents on the agent level. Once, again, the gap between the prototype to production, that once you have a huge scale of agents or applications with using AI, you want to be able to make sure how much it costs, latency, throughput, power, all of those needs to match what the requirements of your application is. Having some quantifiable way to do that is I imagine something that it's like a barrier for enterprises in order to move forward. Like the uncertainty, you don't know how to do like capacity planning for that. I think we need to figure out, and I think also we need to plan to scale in advance. If you know that your organization is have huge demands that keep increasing, you need to build your architecture to do that. Otherwise, when it breaks, it would be very, very painful. I think that fast is the main point is that it's built for scale. It's built for scale. It started built for scale in storage. This is why it's such a successful platform for training. It's built for scale for a lot of the other components that is part of the vast ecosystem. The database, the vector database that will support trillion vectors, the events brokers that is highly scalable and can support millions of events per second. And all of those pieces together with the insight engine and the data engine allows you to build like a pipeline of functions and triggers that is the building blocks that are needed for the agentic AI systems. And especially when you talk about agents at scale that need to be able to communicate with one another very, very efficiently. And the scale would only increase. Those are like a must-have in ecosystem for AI, along with holistic security and identity provisioning. This end-to-end solution is something that is very, very unique for vast systems.